Simulation theory versus multiverse. There are really no other credible options to move forward. Before we can compare those two, I need to first explain to you how science works. Did you notice those blue dots? They have something to do with the dinosaur effect. What is dinosaur effect? I will show you. Which one of these dinosaurs you recognize as Velociraptor? The one on the left or the one on the right? The right answer is the one on the right. According to recent studies, this is how Velociraptors looked like. And if you can see, it is nothing to what we are used to from all the movies and documentaries that we saw. That is because the feathers were discovered in one of the velociraptors. And that is the dinosaur effect in action. We know very little about dinosaurs, yet because of all the documentaries and sometimes even scientific papers, we assume too much about them. We make them look like this, we imagine all these colors of those feathers. Nobody really knows what exact color was. And we imagine how they would make sounds or how they behave. We can get slight understanding of the behavior from the bone structure and such, but we really don't know. So that is dinosaur effect with dinosaurs, but the same effect is actually happens in modern science, unfortunately. So let's look how science works. The dots here represent some measurements that we do, and how scientists try to understand these dots is to build a formula that matches the behavior of these dots. And we could try a few different formulas. The simplest one is y equal x, right? So that would be a straight line. It doesn't match the dots. So let's try something else. Y equals 1 divided by x. It's also not a match. Let's try this one. Y equals x squared. Now that looks much better, right? The formula matches the dots almost perfectly. We have a lot of dots, we know what formula it is. Now look at this. Can you match still a formula to these dots? Yes, you can, possibly, but a little bit less confident now, right? What about this one? Now when we have very few measurements, it's really difficult to apply formula confidently. So what we have? We have a confidence level, and confidence is another word to belief. And is it still a science, really? The process, by the way, is called approximation, so we could approximate this line, but reality can be completely different. It could be like that. Ouch. That is very different from what we thought it is. And now look at this picture. This is a real photograph of scientists trying to interpret particles flying from a collision. Now that is interesting because here we can see a lot of various traces that left in after the collision, and different particles have different energies. So the faster particles will fly straight away in a straight line far away. They have high energy and they're very fast, and some other particles will bend or move in a different direction based on electromagnetic force. So they're sensitive to electromagnetic force. That's how scientists were able to categorize different particles by mass, energy, speed, and of course if they are susceptible to electromagnetic force. So after doing all these experiments and collisions, they counted literally hundreds of types of particles, and it was a mess. So they tried to organize them in categories. Over time, breakthroughs were made. Our brains are amazing, and we can try to find some order in a mess. came up with quite beautiful standard model for elementary particles. So each particle is actually built with a smaller building blocks essentially, and we have all these different types of particles. Recently we confirmed the Higgs boson on the right, and we pretty much feel more or less confident with this model at the moment because it has predictive power. And this table of particles reminded me of periodic table of elements that was discovered a long time ago by scientist Mendeleev. And he actually imagined this table in his dream while sleeping. He knew about all kinds of different elements in nature that were isolated by chemical experiments, and he managed to imagine an order in this complete chaos of elements. That same way we discovered or kind of build this standard model for particles. So this is pretty good, and it does have predictive power. It predicted Higgs boson, and it was discovered just recently. So that's how science works. It's how science works in action. So you might ask, what next? And that's where it gets really interesting, because no matter how beautiful the standard model is, it cannot explain a lot of things. And not just in those collisions in accelerators, but also particles that fly and arrive to our planet from other star systems. And those particles show us really weird things that we cannot explain. And that's what it is really at the moment. We build a standard model, but we noticed that gravity sometimes is a little bit stronger than it should be when we look at all the stars and how gravity bends light and how these galaxies move. So we could clearly see there is more gravity there. So what we're gonna do with that? It doesn't match, the experiment doesn't match the formulas, the model that we built. So we had to invent something. We invented dark matter. It's just another imaginary particle somewhere that adds extra gravity. In math terms, it's just a correction. We just added this extra number in a formula to correct what is not matching the reality. Then dark energy is very similar in that concept. It's a correction for expansion, because we discovered that the universe expanding with acceleration. So why would that happen? Because we have gravity that pulls everything back, and instead it accelerating and expanding. So we had to think, oh, maybe there is some extra energy hiding somewhere. So because we don't know what it is, let's call it dark energy. So it's correction for expansion. Sounds like a band-aid. Another problem. It turns out our universe is very uniform. What it means is there are no super dense areas and super not dense areas. It's kind of all distributed nicely. So Big Bang, if it just exploded from one point, the density should decrease as we expand and rapidly decrease. But that's not what we see, so we had to invent something. So we invented inflation theory, and that says that there was this super quick, faster than light expansion during first moments of the Big Bang to expand it, and then it started to move in a normal way, not at faster than speed of light speed. Just imagination to correct for another weirdness. Okay, that is fine, but we find more weirdness that cannot be explained by standard model. And that is, for example, the cold spot. Google about it, don't have time to explain, or the weaker gravity areas that we see in microwave radiation that arrives to us, and we cannot explain those either. So let's invent something new to patch that as well, and that is multiverse. So multiverse essentially says all these critical constants like gravitational constant and all other constants out there they're only specific to our part of universe, but they can be different in other parts of universe, and therefore different physics laws will be there, and that could explain all the weirdness we see. Okay, fine. They invent other things like holographic universe to explain all these problems with information disappearing in singularity of black holes. How information can just disappear, that's not possible. Or, for example, we invent other dimensions to explain the presence of energy even in vacuum. So maybe that energy is hiding in another dimension, that's why we don't see that. And mirrorverse is similar concept. There is many worlds interpretation. All this interesting imaginative idea, and it is actually how science works. We propose all kinds of wild ideas, and out of these ideas we select the best that best matches the experiment. And that's very important, because if you can match a theory by experiment, then it is a true science, right? And if it has predictive power, your theory, then it is true science. Everything else is speculation. So let's look at all these things. What can be actually proven by experiment? Okay, can we test holographic universe? Not sure. Send me or comment to the video and send me ideas how we would test that, because I tried hard to find any ways to test it and I couldn't. Other dimensions, not possible to test, so let's forget about it. Mirrorverse, there was one experiment mentioned where neutrons would kind of disappear in another dimension and then reappear. I don't know, maybe it's testable, that's why I put a question mark. Many worlds interpretation, not testable. How can you test other worlds? You're not in those worlds. And yes, Missouri is a state in the United States with the slogan "Show me state." So show me, and then I will trust you. So what we left with is really multiverse. That one specifically in interpretation of using some math from string theory and math from standard model, that multiverse, because there are actually multiple versions of multiverse. I'm talking about the mainstream multiverse theory, where we actually use normal particles and try to assume that certain constants in our world are not actually constant in that bubble universes out there. Mathematics. Math is outside of physics in a way. We can beauty in mathematics. And look at the left side. This is how Einstein arrived to E equal mc squared. A beautiful, beautiful small formula. But he had to go through this rigorous and complex and ugly math to arrive to an elegant formula. On the right side we have a golden ratio, which is absolutely beautiful thing, and it will stay beautiful no matter in what kind of world we live in. Symmetry is another universal term. Symmetry is, regardless of physical world we live in, is beautiful. It's symmetry. What we end up with is this gorgeous line, a standard model that has predictive power, was proven in experiment. We can trust it, just like chemical table of chemical elements. And we have a multiverse theory, which is, we spent a few decades on that already, and we do know some pretty good matching experiment things in it. But it also can turn out to be just a patch, band-aid work. It's also possible, and we just don't know at the moment. And then there is this young simulation hypothesis, not even a theory yet. It's a small little cat, because we don't even qualify it as a theory. We don't have rigorous mathematics behind it to prove. Okay, so now to actual comparison between the two. I think both are kind of competing theories, and The fundamental for me is simulation theory assumes creator intelligence behind the creation of our world. Multiverse is godless and doesn't assume intelligent design. In fact, the whole idea of multiverse is that all these beautiful constants of speed of light, gravitational constant, and so on, they were randomly matched to create this world because there are many worlds, and out of these many worlds, this one turned out to be good randomly. They're both testable, surprisingly, but it's true. For multiverse, you can prove existence of other universes analyzing all these cosmic rays that we receive. We just need to build bigger telescopes and probes and so on. Simulation theory is also testable, surprisingly, because all we need to do is direct our experimentation into looking at our world from a digitized, computer-optimized perspective. Our waves are for the purpose to minimize computational complexity and memory usage. Our particles are in random state until they were actually interacted with for the purpose to optimize memory. So you can test them with all this delayed choice experiment or extended versions of quantum eraser experiment and possibly others. So if we didn't spend enough energy in that direction yet, so I'm just encouraging scientists to do that. Multiverse beautiful, arguable. Comment in this video if you think it is. Simulation theory is truly beautiful because it's very elegant, and we'll talk about it in the next video. It explains everything, really. And matches what we see in computer simulations, in 3D worlds that we simulate in a computer. It matches perfectly the quantum physics that we see in real life, so it is beautiful. A lot of research was put in the multiverse already, 2 decades at least. Not great results so far. Almost no research in simulation theory, so I really encourage people to look into that and see what we get out of it. Multiverse cannot explain still why life appeared here, where DNA molecule came from. It cannot explain the weirdness of quantum mechanics still. It can only mathematically explain it in that sense, but it cannot explain the reasons why would the world be like that. Both of those questions are easily answerable in simulation theory. Thank you.